Welcome to this introductory tutorial on CFD-VisCART. In this video tutorial, we will introduce CFD-VisCART, which is a Cartesian mesh generator. The introduction will include information on how this mesh generator works, its unique attributes and inherent advantages. This introduction will include an overview of CFD-VisCART's graphical user interface and information about the various mesh types that are supported. Typically, in the CAE analysis workflow, cleaning up of the geometry and mesh generation consume a big portion of the time. This can also be manually intensive and so ends up being a very expensive workflow component. This is where CFD-VisCART's inherent qualities prove to be very advantageous and result in significant effort and time savings. CFD-VisCART is used to mesh three-dimensional geometries. It generates meshes that can capture the geometry curvatures and features. These meshes have a high percentage of Cartesian cells. Geometries can be imported in one of many supported formats. The intrinsic nature of the mesh generation process, which will be described in more detail shortly, allows automatic handling of dirty CAD data. In other words, CAD cleanup happens automatically and requires little to no manual effort. This cleanup involves generation of a shrink-wrapped mesh to make the model watertight, handle overlapping and intersecting parts and also eliminate unwanted small features. Volume meshes that can be generated include stair-step, single-domain and multi-domain meshes, including boundary layer generation. For efficient production runs, batch scripting capability is available. For faster turnaround time, single-domain meshes can be generated in parallel mode utilizing multiple processors. Let us start working with CFD-VisCART. The CFD-VisCART graphical user interface presents a startup screen that includes quick access buttons to open files, and links to recently accessed files. Let us import a file. In the Import Geometry Files dialog that comes up, let us select STL file type. Then select the file named sphere.stl. Click OK. The imported geometry appears in the Graphics Viewer window. This geometry includes two concentric spheres. The Graphics Viewer also shows a bounding box around the geometry and a domain marker. We will elaborate more about these entities in a few minutes. The two surfaces or patches included in the geometry are listed in the Explorer, below the Graphics Viewer. Selecting a component in the Explorer highlights it in the Graphics Viewer. The Explorer window displays entities based on the selected tab in the Control Panel. The Control Panel is where most of the setup options are located. The Geometry tab in the Control Panel includes the various geometry tools that can be used for geometry editing and manipulation. The next tab in the Control Panel is the Domain tab. This tab provides options to move the existing domain marker or add additional domain markers. The next tab is the Source tab. This tab provides options to add various types of mesh sources to refine the mesh at desired locations. Mesh source types include point source, line source, curve source, plane source, surface source, box source, sphere source, cylinder source and region source. The next tab is the Gap tab. This tab provides options to identify gaps between adjoining parts that need to be resolved, including the approximate number of cells to be generated in each of these gaps. The next tab is the Patch tab. This tab provides options to specify mesh properties on a patch-by-patch or surface-by-surface basis. A number of options are available including local mesh refinement, local body fit factor, local feature preservation, refinement near high curvatures, among others. The next tab is the Grid tab. This tab houses the mesh quality improvement tools, which show up only after a mesh has been generated. We will go over this tab in a few minutes. Let us take a few moments to understand the meshing process in CFD-VisCART. In conventional mesh generators, the surface is meshed first and then the volume mesh grown from it. CFD-VisCART follows a different approach. The available volume, the bounding box, is first filled with cells, and then the cells near the geometry are projected or placed on the geometry surfaces to generate the surface mesh. The following schematic provides an approximate representation of the meshing process. It also identifies the various types of meshes that can be generated using CFD-VisCART. Say, for example, a mesh is to be generated around a sphere. During the meshing process, first, the entire bounding box is filled with cells. Then the intersecting and interior cells are removed. The cell nodes near the geometry are then projected on it to capture the curvatures of the geometry. The image at the center represents a stair-step mesh. The image on the right represents a single-domain mesh. The surface mesh generated by means of projecting nodes represents a shrink-wrap mesh. Now, if a mesh is to be generated both inside and outside the sphere, a slightly different approach is used. After the bounding box is filled with cells, the interior, exterior and intersecting cells are identified. Then some of the cells near the geometry are split and certain nodes move to capture the curvatures of the geometry. This represents a multi-domain mesh. Let us go over each of these mesh types and highlight their usage and applications. Stair-step meshing is typically used to generate a relatively low cell count mesh for preliminary studies. For simulations where wall effects are not important, this type of a mesh could also be used for final analysis. Generating a stair-step mesh can also serve as a quick and useful method to determine desired mesh resolution prior to generating a body-fitted single-domain or multi-domain mesh. The projected single-domain mesh, which is a body-fitted mesh, has wide-ranging applications, typically where only the fluid domain needs to be meshed. Listed here are only a few of the many application areas where single-domain meshes are employed. The projected single-domain mesher provides a number of advanced meshing features. Some of these features will be covered in this and other CFD-VisCART tutorials. The multi-domain mesh, which is also a body-fitted mesh, has wide-ranging applications, typically where multiple domains are to be meshed and simulated. A number of advanced meshing options are available with this mesher. Some of these features will be covered in this and other CFD-VisCART tutorials. A shrink-wrap surface mesh is typically generated to cover, or clean up dirty geometry, that includes holes, gaps, cracks, or other geometry imperfections. It can also be used to generate a lower resolution surface, if fine details in the original surface are not essential to a simulation. Let us go back to working with CFD-VisCART. The bounding box serves the purpose as explained in the schematic. The domain marker serves to identify the region that needs to be meshed. For example, the current location of the domain marker implies that the mesh needs to be generated around the outer sphere, not inside it. The CFD-VisCART toolbar includes shortcuts to the most frequently used functions. In the toolbar, click on the bounding box setting icon. A dialog comes up in which the bounding box dimensions can be specified. The bounding box size can be specified in terms of factors of geometry size or in terms of actual min and max location in each of the 3 coordinate directions. We will retain the default values for this case. In the toolbar, click the Generate Mesh icon. The Generate Mesh dialog comes up. This is the dialog where all the global mesh parameters are specified. Let us specify mesh type as stair-step. We will retain the default selection for Cartesian tree type, omnitree. Although the octree approach provides more uniformity in cell sizes in all directions, it leads to a significantly higher cell count compared to the omnitree approach. Cell sizes in CFD-VisCART are usually specified in terms of levels. Detailed information about levels is provided in subsequent tutorials. Simply putting it, the higher the level number, the smaller the cell size. The cell size corresponding to each level is also shown next to it. The minimum division level specifies the maximum cell size that is allowed anywhere in the mesh. Under the Boundary Refinement tab, the cell sizes to be generated at the geometry surfaces or boundaries are specified. There is also an Advanced tab for advanced mesh settings, but for this case, we will not specify any advanced parameters. All settings in this dialog are global parameters and apply to the entire model. As mentioned earlier, local mesh parameters can be specified under the Patch tab in the Control panel. In this case, we are not specifying any local mesh parameters. So, let us go ahead and click Generate Mesh. Once the mesh is generated, the cell count is shown in the Explorer. Note that because we are generating a stair-step mesh, there are no other mesh statistics reported here. But for single-domain and multi-domain meshes, additional mesh statistics will be reported together with the cell count. The entity bar provides options for geometry and grid blanking, visually scaling and rotating the model, cut planes, among others. Cut planes can be used here to view the generated mesh, by sliding them through the model. We can also specify a location of the cut plane by typing in the value. Let us place the z-cut plane at z equals 25. The cut plane appears showing the mesh. Zooming in, we can see the jagged or stair-step nature of the mesh. Blanking the geometry surfaces can help better visualize the mesh on the cut plane. Using options in the Geometry and Grid Blanking tab, the jagged surface mesh can also be viewed. Although stair-step meshes involve jagged boundaries, they are of very high quality, and as mentioned earlier, they can be used during preliminary analysis, or for studies where the physics near the walls are not very important. Next, let us try generating a projected single-domain mesh, in which the curvatures of the geometry surfaces are captured and no jaggedness exists. Let us change the mesh type to projected single-domain. A number of advanced options exist for single-domain mesh generation. We will keep all default settings for this exercise. Let us click the Generate Mesh button to start mesh generation. Once the mesh has been generated, you can see that the spherical surface has been properly captured. In single-domain meshing, the projection of cells to capture the geometry curvatures results in the creation of non-Cartesian cells. To ensure that these cells are of good quality, the mesh should be improved using the Mesh Quality Detection and Improvement tool in the Grid tab. Note that the Explorer displays not only the cell count but also a number of mesh quality statistics pertaining to the generated mesh. Now let us drag the domain marker inside the sphere and regenerate the mesh. In an orthogonal viewing mode, double-click and drag the domain marker towards the center of the model. Switch to another orthogonal view, and double-click and drag the domain marker to the center of the model to make sure it now lies within the inner sphere. To verify that the domain marker lies within the inner sphere, we can use the clip option with the cut plane. The clip option clips the part of the model that lies in front of the cut plane, allowing better visualization of what lies inside. We can see now that the domain marker is inside the inner sphere. The mesh still appears outside as the previously generated mesh has not been deleted. Let us regenerate the mesh. When we do so, the mesher will recognize the new position of the domain marker and generate the mesh only inside the inner sphere. As we see here, the mesh has been generated only inside the inner sphere. As before, the quality of the mesh should be detected and improved before it is saved. Now let us try to generate a multi-domain mesh that includes 3 domains. One inside the inner sphere, one between the 2 spheres, and one between the outer sphere and the bounding box. We already have a domain marker inside the inner sphere. Let us add a domain marker between the inner and outer spheres. The second domain marker, domain 2, has been added at a default location. Just like we did earlier, we will drag it to a location between the 2 spheres. Let us add a third domain marker, and retain it, outside the outer sphere. Let us click the Generate Mesh icon in the toolbar. As the model now includes 3 domain markers, the projected single domain meshing option is no longer available. We will select the multi-domain meshing option. With this meshing option too, several advanced options are available. We will retain the default settings for them. Let us generate the multi-domain mesh. Once the mesh has been generated, you will see the mesh in all the 3 regions, colored differently for easy visualization. Let us detect and improve the mesh quality. Once the mesh has been generated and improved, we can save the mesh in DTF format by clicking the Save As icon. This concludes our introduction and overview video. We encourage you to go through the rest of the tutorials that we have prepared. These tutorials cover in more detail the various measures and features of CFD-VisCART. If you have any questions regarding this tutorial or any other topic, please do not hesitate to contact ESI CFD customer support. Thank you for viewing this video tutorial. We hope you found it helpful.